Good morning, guys. Today we're going to expand on our last lesson where we talked about what the idea of probability is by getting in and actually doing something we haven't done in a while, which is some actual math calculations. So we're going to start calculating some very basic probabilities. Before we can do that, we need to hit a couple of definitions first. So here's our problem. Consider rolling a standard six-sided dice one time. Look for the probability that one roll produces an even number. So there are two things happening here. We have what we call an event and a sample space. An event is just a specific outcome of a chance process. We talked last time about what a chance process is, but just something where anything's possible. So an event is one of the specific things that can occur. So in this case, the thing that we're wanting to occur is rolling an even number. That's going to be our specific outcome that we're looking for. So that would be our event. So if we listed out the possible outcomes that would make that successful, we could roll a 2, we could roll a 4, or we could roll a 6. All of these would make our event, or would match our event. Next we have sample space. Well, if the event is what we're looking for happening, the sample space is anything that can happen. So it's all possible outcomes of a chance process. So in this scenario, what would be our sample space? Well, all possible outcomes on a standard six-sided dice would be rolling a 1, a 2, a 3, a 4, a 5, or a 6. All of those are possible. All right, so let's go in and let's use this event and this sample space to do some just basic probability. Now, basic probability, you've been working with this for I don't know how many years, but it's number of outcomes corresponding to the event divided by number of outcomes in the sample space. So it's how often we should be successful, right? If all these things are supposed to occur at even rates or representative rates, how often would we get this specific outcome through many, many, many trials? So a more general definition that you may see is just success over possible. So using that, let's go through a couple of probabilities. So first one we've got here, probability of rolling a 7. Probability of rolling a 7. So if I do my outcomes corresponding to the event, what all on a regular six-sided dice can I get, or what are all the different ways I can roll a 7? Well, I can't roll it anyway. So there are no possible outcomes there, or sorry, no successful outcomes. So our possible, though, is still 1, 2, 3, 4, 5, or 6. So in this problem, there would be 0 chances of being successful out of 6 possible outcomes. So there's a probability of 0 for rolling a 7. All right, what about rolling a number 1 through 6? So a successful outcome would be rolling either a 1, a 2, a 3, a 4, a 5, or a 6. All of those would be successful because all of them match up to our event. Possible is still 1, 2, 3, 4, 5, 6. So how many possible outcomes are successful? 6 of them. How many possible outcomes are possible? 6 of them. So we get a probability of 1. So this means this is if nothing can happen. This is if everything can happen. So that should give us an indicator that probability is always between 0 and 1. So if we ever see a situation where probability is negative or probability is over 1 or things like that, we're not dealing with a true definition of probability. So there's something else going on in that case. So probability needs between 0 and 1. All right, now let's do just a regular one. Let's do this probability of rolling an even number. So we talked before, our event would be, successful event would be 2, 4, or 6. Possible would be any of those numbers 1 through 6. So that's 3 successes over 6 possible. So 0.50, a number between 1 and 0. So that's probability of rolling an even number. That's just the general basic definition of probability. Now, another aspect of probability we often work with, and we actually worked with it back when we were working with normal distributions, is this idea of complement of a probability. So what do we mean when we say complement? Complement works off this definition right here. Probability of A plus the probability of AC, that's A complement. And then this is the notation that we use. Sometimes you'll see just like a tick mark there, something like that. So, but this, we would call it complement, or sorry, A complement, or complement of A. I call that A complement, or we could just call it not A. That's how I'll often refer to it. So the probability of everything that's successful plus the probability of everything that's not successful should equal 1. That's what complement means. It's just saying that altogether we've got to account for 100% of our probability when we're adding in the complement. Now, a couple of little extensions on that. Probability of A can be 1 minus the probability of A complement, or we could go the other way, probability of A complement 1 minus the probability of A. Now, how did we use this before? Remember when we were doing our inverse norm information, we were trying to get things into the calculator correctly? We said if they gave us the top 30% and we needed to key in the calculator, we had to do the bottom 70%. That's what we were doing. We were working with the complement. So that 70 for the area that we typed in was the complement of the 30% that they had given us. All right, so that's what all complement is. They give you one piece of information, but you need the other side of it, so we're just going to subtract it from 100%. You want everything that's not in that. So general probability rule and complement of probability. Now let's look at how we can do a little bit, get more involved with probability and look at multiple events. All right, so if we're looking at multiple events, there's a lot of different ways we can deal with them. We can have independent events, dependent events, mutually exclusive, non-mutually exclusive. We're going to focus mutually exclusive and non-mutually exclusive today. Next lesson we'll talk dependent and independent. So a mutually exclusive and non-mutually exclusive. That means that we're selecting one item or object or person, or we're doing one thing. Okay? And what we're trying to do is, after we've done that one thing, we're trying to see how many characteristics does that object belong to. So select one object and then determine how many characteristics does that object satisfy. How many characteristics does it satisfy? So, for example, if we did something like selecting one student from a class, and then we wanted to know the probability, the characteristics were being in the bathroom or being in the classroom. Okay? Those would be two events. We want to know, does that student satisfy the being in the classroom category or the being in the bathroom category? That's kind of the thing that we're talking about. Now, if it's a situation like that, is it possible to both be in the classroom and in the bathroom at the same time? No, that object, that student, can't satisfy both of those characteristics. So that would be an example of mutually exclusive events. That's when the object can only belong to one group. That object can only belong to one group. So, being in class and being in the bathroom. Now, a non-mutually exclusive event would be something where the object can belong to multiple groups. So for example, say that my events were being a stats student and being an athlete. Is it possible for a student to both be an athlete and be a statistics student? Yes, that's possible. So those would be non-mutually exclusive. One event does not exclude you from the other, whereas these were mutually exclusive events. Being in the class excluded you from being in the bathroom, and vice versa. So these multiple events, if we want to work with how to see if objects or events can satisfy multiple characteristics at once, we need to look at how we can kind of combine those together. So that's what the general addition rule does for us. So general addition, probability of A or B. So the probability that we satisfy either event 1 or event 2. So you'll often see it written like this, A and then this letter U, that is known as union. Union. And all union just says is, does it fit this one or this one? If it fits either one of them, then it says a successful outcome. So the way we can get that, if I wanted to know the probability of being a stat student or being an athlete, right? If you're a stat student, you're a check, right? If you're an athlete, you're a check. So all the stat students would be considered a success. All the athletes would be considered a success. But some athletes, or some people got counted as both a stat student and an athlete. As we talked before, you have to stay between 0 and 1. I can't count people multiple times because then that may make my probability get over 1. So that's what this minus does. Take event A plus event B, that's all you're doing with an OR statement or a union statement, minus A intersect B. That's what that little symbol means. It means intersection. And intersection is just another way of saying and. So we take the individual events minus anybody that got counted twice. So my athletes got counted here, my stat students got counted here. I'm just going to subtract out one of the extra times that I counted them. So that's why I'm minus anybody that got counted twice. All right, so let's go through a couple of examples. Okay. So probability of an even number or a number greater than 3. Even number or a number greater than 3. So event 1 is probability of even. Event 2, probability of number greater than 3 minus a both. Well, what would a both look like in this case? It would be an even number greater than 3. An even number greater than 3. So going through our probability rules, how many even numbers are there on the dice? 2, 4, and 6, right? So I got 2, 4, 4, 6. Out of all those numbers 1 through 6, okay. How many numbers are greater than 3? 4, 5, and 6. Out of all those numbers 1 through 6, minus anybody got counted twice. How many even numbers were greater than 3? Well, 4 and 6. So see how 4 and 6 got counted here and here. I'm just going to count out the extra time, or subtract out the extra time they got counted. So subtract the 4 and 6 out of all possible. So when we do that, what do we get? We get 3 out of 6 plus 3 out of 6 minus 2 out of 6. So that's going to give us 4 out of 6, which is 0.67. So that's the probability when we roll a dice of rolling either an even number or a number greater than 3. So 2/3 chance. All right, so pause it right here. Take a second. I want you guys to see if you can come up with this probability right here. Hopefully you got this answer here. Okay, so probability of getting a number less than or equal to 2, well, there are two of them, 1 and 2, plus probability of getting a number greater than or equal to 4, so there are 3 of them, that's 4, 5, and 6, minus the probability of getting a number that's both less than or equal to 2 and greater than or equal to 4. So in this case, that would be 0 numbers. There are 0 numbers on the dice that are both less than 2 and greater than 4, so there's nothing to subtract. So this would be an example of what type of event? Mutually exclusive or non-mutually exclusive? Yeah, that would be a mutually exclusive event because you can't be both at the same time. So when we add it all together, we get a 0.83 for that probability. All right, so that's general addition rule. When you see or, you want to think add. Okay? When you see and, you want to think what do they have in common. But we'll talk more about ands in the next section. All right, next I'm going to look at another way that we can kind of expand on this idea of complements and unions and intersections. All right, let's talk Venn diagrams. These should look familiar to you. You've been using them probably in English courses and things like that before. So what do we use Venn diagrams? Venn diagrams allow us to visually describe similarities and differences. Similarities and differences. So we like to think of it in terms of these complements. What is in an event, what is not an event? What's a success and what's a failure or a non-success? So a Venn diagram of a complement situation would look like this. Here's A, and this is everything that's not in A, and all of it together equals 100% of the probability that something is going to happen. So it's a visual of complement. All right, so mutually exclusive events. What do mutually exclusive events look like? Well, mutually exclusive events say that A and B don't have anything in common. There's no overlap between them. All right, so if there's nothing in common, their circles are not going to overlap. So their intersection is going to be empty. Okay, so the empty set would be their intersection. And we can see all this stuff that's outside. It says A complement intersect B complement. Well, what does that mean? Well, that means where everything is not in A and it's also not in B. So it's in neither A nor B. That's what that stuff out there. And then last we have the picture of a non-mutually exclusive event. Non-mutually exclusive means they do not exclude each other. Okay, so if they do not exclude each other, there can be there is some type of overlap to them. And so that's what we see right here. A intersect B is this section where the two cross each other. So where the red and blue cross, that's going to be the intersection where both those groups, both those events have individuals that are in common. Now, I want to look at A union B, not as just an addition rule situation, but I want to look at it as kind of an addition of components. So let's look at this Venn diagram up here. So if I said A or B, the probability that something happens in A or it happens in B, can I not just take these individual areas and add them together? So instead of trying to subtract out, let's just never even factor those things in. So if I have an A union B situation, anybody that would be successful would be something that's in A, right? Okay? It's got to be in A, but not in B. Would that be a success? If I'm doing A union B, that would be successful to have elements that are in just A. They would be considered a success. Okay, well, what are some other successes? Well, what if I have things that are in just B? So if they're in just B, but not A, okay, just B, but not A, those would also be considered successes. Right? So anybody that's in A alone, successful. Anything that's in B alone, successful. Well, anything that's in both of them, so anything that's in both A and B, would also be considered a success in this case. So these are the three areas that fit in the A union or A or B, right? Anybody in this blue only would be considered a successful outcome. Anybody in the purple region and anybody in that red region right there. So we could really think of this as A intersect B complement, right? That's what A and no B's at all. We could think of this as A complement intersect B, no A's, but everybody in B, and then A intersect B. So instead of taking each individual probability and looking at them as separate events and then trying to figure out where they overlap, let's just add up all the individual pieces that we have there. So if we were to take those three areas together, that would give us our probability of A union B. That's the same thing as A union B, those three areas alone. Now there's a faster way that you could do that, because if I'm wanting this area plus this area plus this area, would it not be easier to use that idea of complement and say, why don't we just dump all of this stuff on the outside? Then it would only leave us the inside. So all that is the same thing as saying take 1 minus everything that's not in A and not in B. Not in A and not in B. That is another way that we can calculate the probability of A union B. So we can do it as a general addition rule, we can do it by pieces, or we can do it as, let's just subtract everything that's not there, or everything that we don't want. All right, so give me a second, I'm gonna put up a couple of examples so we can kind of work through that with some actual numbers and a problem. So here we have our example. Consider drawing a card from a shuffled standard deck of 52 playing cards. All right, so let's quickly go over what's in a standard deck of 52 cards. There are 4 suits, which are 13 cards each, 2 colors, red and black, which are 26 cards each. Each suit has 3 face cards, jack, queen, king, 1 ace, and 9 number cards, numbered 2 through 10. All right, so we have 2 events here. Event A, the card that's drawn is an ace. Event B, the card that's drawn is a heart. So we're going to go through how to use general addition rule and how to use these Venn diagrams to try to figure out these multiple events, this A union B. So we're going to use general addition rule first to find the probability of A union B. So probability of A union B. Well, what is probability of A? A was the event that we get an ace. And we want to look at how that relates to getting a heart. An ace or a heart. Now, we remember that A union B is going to be OR, right? That just tells us to add them individually. So we do probability of an ace plus probability of a heart minus anybody that got counted twice. So that's probability of both. And what's both? Well, both would be an ace of hearts. All right, so what was probability of an ace? Well, it told us right here that there's 1 ace in each suit, and there are 4 suits, so you have 4 aces out of the 52 cards. Probability of getting a heart. Well, a heart is one of our suits, right? So there are 13 hearts, because there's 13 in each, out of 52 cards, minus being both an ace and a heart, which is our 1 ace of hearts. So they get counted as an ace and they get counted as a heart, so we're just going to subtract out the extra time we counted it. So when we go through and do all those calculations, 4, 13, right, minus 1, so that's going to give us 16 out of 52, which is approximately 0.31. So that's going to be our probability. So that's using general addition. All right, let's go in and see if we can kind of come at the same answer from a different perspective. So let's go to the, first let's make a two-way table. So number two-way table is just how we can organize 2 categorical variables. So in this case, being a heart or being an ace. So on my rows, I'll record being an ace or ace complement, not an ace. All right, so how many aces are, and then we want to have our hearts. So being a heart or not a heart. All right, now I want you guys to just take a minute. I want to see if y'all can complete this table right here. So I'll wait right here, pause the video, and see if you can fill in this two-way table of breaking down a deck of cards and drawing one card into being an ace or a heart or not. All right, hopefully you got something that looks like this. All right, as we can see, we have one ace of hearts. We have 3 aces that are not hearts for 4 total aces. We have 12 hearts that are not aces. All right, so we have the 1 heart that was an ace, and then 12 more hearts that are not aces, giving us 13 total hearts. And then that leaves us with 36 cards that are not an ace and not a heart. That's what this 36 represents. All right, so this is how we can fill in that two-way table. Let's use that two-way table and build a Venn diagram then of the same situation. So I've got my 2 events. Now in this Venn diagram, actually I'm gonna pause. I'm gonna let you guys try to create a Venn diagram to represent drawing 1 card, but looking at the 2 events. A, it's an ace, or B, it's a heart. So pause it right here, and I'll give you a second to work on that. All right, hopefully you got something that looks like this. Yes, as we can see, we have our ace and our heart should overlap because there is an intersection between the 2. That's the 1 ace of hearts, so that's in the intersection area. We have 3 out of the 52 cards that are ace only, 12 out of the 52 that are heart only, and that leaves us 36 out of the 52 that are neither an ace nor a heart. Now, let's put these 2 together and try to figure out A union B, which is just ace or heart. That's all A union B means. Probability of ace or heart. So we could be an ace only, we could be a heart only, or we could be an ace and heart. All 3 of those would satisfy being at least an ace or a heart. So our ace only group would be the 3 out of 52. Our heart only group would be the 12 out of 52. And then our ace and heart group is the 1 out of 52, which all that totaled up, 3, 12, 1, gives us 16 out of 52, which is at 0.31. 0.31. There's another way we could have figured out the total area, because that's really all we're doing. What's the total area of these 2 circles with making sure not to count that middle twice? So if I want that total area, couldn't I just do complement where we subtract the part that we don't want? So this is the same thing as if I'd just done 1 minus the 36 out of 52 that I didn't want. And this is where complement is very useful. Because here I needed to find 3 values to be able to figure out ace or heart, or I can figure out 1 value and then just subtract it from the 100%, from the 1 whole. So if we do that, that gives us our 16 out of 52, which is the 0.31. So what we can say is ace or heart is the same thing as 1 minus the probability of not an ace and not a heart. So these are equivalent statements. So we have a variety of ways we can go about calculating probabilities of multiple events like this. We can use general addition rule, or if we've got our data organized in the 2-way table already or in a Venn diagram, we can use this addition or complement rule to just add the pieces that we need or subtract from 1. All right, that's it for basic probability rules, and I will see you in class tomorrow, guys.